Thanks, Yuri. It's a pleasure to be here to talk about not only gravitational waves from a multi-messenger perspective, but also a pan-spectral perspective that is across the entire landscape of gravitational waves. Honestly, I can't remember when I didn't think that gravitational waves and black holes were these incredible exotic phenomena. And I think it's a privilege that I get to be active in research at a time when we can directly measure and detect these objects, because let's face it, black holes are incredibly cool. So the fact that we can directly observe these objects now interact with each other in otherwise dark systems is an incredible opportunity. So I'm going to lay out what I've been working on over the last number of years in LIGO and Virgo, and also in pulsar timing arrays, and then what I see as some exciting trajectories for the future. So first of all, I'll cover some themes throughout this talk. First of all, where did LIGO's black holes come from? What kind of systems gave birth to these black holes? What can black holes tell us about fundamental physics, cosmology, and even dark energy? What is the future of gravitational wave astronomy in the next couple of decades? Ooh. How can pulsar observations inform us about the most massive black holes in the universe? And then, somewhat as a non sequitur, what is the nature of dark matter, which is something pulsar timing arrays can also prove. So in more detail, I'll cover, first of all, the gravitational wave landscape, which I'm sure you're all completely aware of, but I'll give a brief primer. Then my activities in stellar mass black hole observations with LIGO and Virgo, which is ground-based gravitational wave detection. Within that, I'll talk about how we can constrain the Hubble constant and other cosmological parameters using catalogs of gravitational wave detections, and how we solve the inverse problem of stellar evolution and the physics of the different pathways using these catalogs. Then at much, much lower frequencies and much greater mass scales, we've got galactic scale gravitational wave detection of supermassive black hole binaries. These are 10 to the 8 to 10 to the 10 solar mass systems. And within that, we can constrain the dynamics and demographics of these supermassive black hole systems. And then also, it's treated as a noise source for us, but it's an incredible side opportunity in planetary science as well, how we create a pulsar timing calibrated model of the solar system, which is incredibly important for PTAs. And within each of these different factors, I'll explain some exciting future opportunities. First of all, we're going to talk about gravitational waves. I'm sure I don't need to describe this, but anyway. Within general relativity, gravity is described as deformed space-time geometry, where freely falling particles move along geodesics of some background space-time, described by the metric tensor G mu nu. However, if you make perturbations to this background space-time, then that will emit wave solutions. These wave solutions propagate at the speed of light, and these are known as gravitational waves. Within general relativity, we have two possible polarizations of these gravitational waves, named for how they deform space-time in the plane perpendicular to the direction of propagation. This is the plus mode, this is the cross mode. They are offset in angle by 45 degrees, and the gravitational wave in this case would be propagated into or out of the screen. And this is trying to show the same effect in 3 dimensions, but this is too unsettling to dwell on for too long, so let's move on. The classic example of gravitational waves emanated from a system is from a binary system of compact objects. The amplitude of the gravitational wave emission from these systems, which is the stretching and squeezing factor as the gravitational wave propagates, in a binary system is proportional to the mass of the system to 5/3, the orbital frequency of the system to 2/3, and then inversely proportional to the distance to that object. Now, this relationship is incredibly important. Remember that for the future, because it gives us a way to measure cosmological distances in a way that's calibrated entirely by fundamental physics. That is our understanding of gravity. So let's set this system running. We've got two black holes orbiting each other. As they orbit each other, they're emitting gravitational waves. That causes the orbit to tighten because the orbital energy is reduced. As they tighten, their orbital frequency increases, so does the amplitude of the emission, until eventually you get a merger to form a final, even bigger black hole. This is showing the same thing from a different perspective, and then this is showing the strain signal in plus and cross, those two different polarization states that I talked about. And you can see what's happening here. You've got something that looks initially sinusoidal, but then as it goes on, the frequency is increasing, the amplitude is increasing. This is called the chirping, like birds chirping. I'm not going to do it because it would be embarrassing, but you get the broad idea that the amplitude and frequency is increasing until the merger. Now, black holes are actually incredibly simple objects, the most simple objects in the universe, and so the waveforms depend only on a few things. The mass, the spin, and the electric charge. But astrophysical black holes don't hold on to their charge very easily, and so they are described almost entirely by their mass and spin. In case you're wondering, this is mass, spin, electric charge. There are some interesting interactions between the spin of the black holes and the orbital angular momentum of the binary. For example, if you have two spins aligned with the orbital angular momentum, you'll actually get a delayed merger. That's called an orbital hang-up. It's really the fact that the ISCO for spinning black holes is smaller, so they orbit each other for longer. And if you get the orbital angular momentum misaligned with the spins, you get a more prompt merger. Now, neutron star waveforms depend on the nuclear equation of state, so they're a bit more complicated. They tidally deform each other. They actually raise tides in each other, which sucks energy out of the orbit and causes a more prompt merger than you would get for an equivalent system of black holes. But unlike black holes, you actually do get a plethora of electromagnetic signals across the entire spectrum, and this was actually observed with one of LIGO's detections, GW170817. A collision of two neutron stars resulting in a short gamma ray burst and an entire range of observations in the optical, UV, X-ray, gamma ray. It's been observed with the entire band. So I've been discussing stellar mass black holes and neutron stars up until now, so let me divert into more detail about ground-based gravitational wave detection of these systems. So LIGO, I'm sure you know, is a 4-kilometer long L-shaped laser interferometer. There's one in Hanford in Washington, there's one in Livingston, Louisiana, but there's an expanding global network of these observatories also. There is Virgo, which has been operational for the last few years in advanced mode, joining LIGO in Hunts already, GEO600 in Germany. This year, hopefully, Kygra will come online in Japan, and then in the early 2020s, we'll have LIGO India come online. And this global network helps in cross-validation, but also in adding information to the waveform parameter estimation. Now, LIGO works through the differential stretching and squeezing of the arms caused by the gravitational wave. A gravitational wave coming in will, and impinging on the detector, will stretch one arm and squeeze the other, causing a laser beam which is initially in phase and being split to come back out of phase and produce an interference pattern at the photometer. So all the information about the gravitational wave emitting system is in that interference pattern, plus some timing information between the two sites helps with scale localization. Again, for those not in the know, gravitational waves have been discovered several years ago. This was a very loud binary coalescence. The corresponding masses of the objects were too large to be consistent with neutron stars. These were two gigantic black holes in the stellar mass class. And the signal was in band for roughly 200 milliseconds. So all of the action in LIGO happens on the scale of a couple of hundred milliseconds. And this was not a threshold event. This was an order signal to noise 24. Since that time, 9 more binary black hole coalescences have been detected, and a double neutron star collision. So one of these newer ones, announced within the last 2 months or so, I guess it's 3 months now, it was early December, GW170729 is a contender for the most massive black hole found in a binary system, having one of the black holes being 50 solar masses. And so that's right on the edge of where you'd expect there to be a mass gap from parent stability processes in supernova. So this is a compelling system in terms of stellar evolution. Another interesting system, and they're all special, but these are two of the particularly interesting ones. GW170817 is a double neutron star, which resulted not only in gravitational wave detection, but in broadband electromagnetic follow-up, and as I'll explain soon, a measurement of the Hubble constant. But as you can see here, all of these binary black holes and the resulting black holes seem quite heavy compared to the X-ray binary black holes that have been measured before. The neutron stars are broadly consistent with what's been measured before, but LIGO is sitting right up here compared to other black hole measurements. So this got me interested, and many other people interested also, in hunting down the progenitor conditions of stars that could give birth to these black holes that eventually merged to form LIGO detections. So this is what I'm calling gravitational wave stellar genealogy, trying to find the parent conditions of stars that give birth to these LIGO detections. There are a variety of different formation mechanisms and evolutionary channels. One is isolated binary stellar evolution, where you've got two stars in a binary system in the field that are orbiting each other and undergoing separate evolutionary processes, eventually forming two black holes. Another option is dynamical formation in a dense stellar cluster environment, where you've got lots of black holes gravitationally snagging other black holes and forming binary systems. That's an efficient way to build up large mass black holes also. And There are other mechanisms at play. One other mechanism could be chemically homogeneous evolution in a tight binary, where you've got two very close together stars, which actually tidally deform each other. They churn up material inside each other, so you don't get a strict demarcation between the core and the envelope. This will actually stop a lot of mass transfer between the systems, and so the stars will individually hold on to a lot of mass and form correspondingly more massive black holes at the end. Now, what I'm particularly interested in is isolated binary stellar evolution. And this is one particular possible track for two main sequence stars evolving into binary black holes. So this is two main sequence stars. The primary will evolve off the main sequence and form a red giant, undergoing a mass transfer phase to the secondary, leaving a naked helium core. That will then either undergo direct collapse or a supernova to form the black hole, the initial black hole. Now, the secondary will also evolve off the main sequence, but this time the mass transfer to the primary black hole will be dynamically unstable. It simply can't accrete all of the material, and so the black hole is engulfed by the envelope of this secondary, and you get a common envelope phase. This common envelope phase is actually incredibly important in tightening the binary to be observable within a Hubble time. You can see before the common envelope phase, you're at a couple of thousand solar radii separation. After that, you're down to tens. So this is very important in bringing the stars together and forming black holes that actually merge in enough time that LIGO can detect them. So after that phase, you get direct collapse or some sort of supernova forming the binary black hole. Now, there's a lot of play here. There are complex physical processes going on. But there are a couple of key factors which really influence the rates and final demographic properties of the black holes. The first will be the progenitor metallicity. Metallicity is obviously anything heavier than helium. Low metallicity stars will tend to suffer less wind loss throughout their lifetimes and will retain more of their mass. So at the end, they will form heavier black holes. Also, high supernova kicks in any of these particular scenarios could potentially unbind the binary and dramatically diminish the rates. And then this process, again, is very important in bringing the stars together. This is the efficiency of the common envelope viscous drag phase. So high efficiency is needed to reduce that orbital separation. And what you might want to do to bring all of this complex physics into play is take your catalog of LIGO's detected binary black holes, then run lots and lots of different stellar population simulations, trying to understand the demographics that result from each of your simulations, and looking which one gives you the closest to the initial, which one gives you the closest to the final LIGO catalog. That's actually a really inefficient and strenuous process because these simulations, they take a long time. They can take days or weeks, so you might only be able to run a handful of these simulations. What you really want is something that's fast enough that can emulate the demographic properties of the binary black holes as a function of the initial stellar conditions. And that's fast enough that you can actually slot into some sort of Bayesian catalog analysis. And that's what I've built. It's an emulator of binary black hole population properties as a function of stellar initial conditions and binary initial conditions. So we ran a bank of binary stellar evolution simulations at representative points in metallicity space, supernova kick magnitude, and the efficiency of common envelope evolution. We then tagged the features of the black hole mass and redshift distributions as a function of those initial conditions. It's essentially doing principal component analysis on these distributions as a function of the initial conditions, and then interpolating the weights of those features across the hyperparameter space, or the initial condition space. And this builds a very fast emulator of the full population synthesis that you can then use to analyze the full LIGO Virgo catalog. That's what we did. And metallicity is the parameter that's most compelling here. What we found is that the LIGO Virgo catalog as of December, which was only about 5 binary black holes, is favoring progenitors with lower than 10% solar metallicity at 90% credibility. And I'm quoting credibility here because this is actually recovering the posterior distributions of the initial conditions of the stars and the binaries. Now you can actually take this even further and try to match up what kind of host galaxies these systems could have come from. You need a low metallicity galaxy, you need a low metallicity star, so low metallicity stars will form in low metallicity galactic environments, which will typically be closer by dwarf galaxies or potentially farther massive galaxies. But our results seem to be favoring progenitors from these low metallicity type systems. And this is the recovered underlying distribution of masses, chirp masses, and merger redshifts from the LIGO Virgo catalog. This is only with the handful that existed in December. But you can see they're tracking the distribution quite well, and LIGO still doesn't have a redshift reach to really pin this down, but this shape is constructed from the population synthesis, which is constrained at the lower redshift.
If this is assuming that you understand the winds from stars attached to this statement, and so.
Right, and it has been updated. You know, it's something that's been updated from the LIGO observations themselves. We saw that there were 30 solar mass black holes, which not many stellar population simulations could produce, and so the codes had to be updated. So it's very much something that's proceeding in tandem. The physics has been updated simultaneously with the inference. And rather than taking a very model-dependent simulation process like this, you could also make an agnostic recovery, which is what LIGO does, actually just recovering the distributions of masses and redshifts underlying the population. Now, it's not just the astrophysics of the stellar population you can probe, it's also cosmology. So this is showing the representation of the extragalactic distance ladder to get to the Hubble constant. This is not showing the CMB, this is showing techniques like Type 1a supernova and Tully-Fisher. And most of these techniques rely on either empirical relationships or some sort of calibration process to move into the Hubble flow. Now, the Hubble constant is just relating the precession speed of the galaxies to their distance from us, but a compelling alternative is gravitational waves. Remember, I said that they directly encode the distance of the systems, so the strain amplitude is inversely proportional to that distance. So to probe the Hubble constant, all you need is an independent measure of the redshift of the system, which will give you the recession speed. This is actually what LIGO has done recently. This is showing the Bayesian posterior distribution of the Hubble constant from the double neutron star detection, 1708-17, which had an associated host galaxy, NGC 4993.
From the digression on the distance, there was a suggestion that some of them were gravitationally lensed. Do you think that has any merit?
I think that's been disputed quite heavily in the community. I think that's been disputed quite heavily in the literature. The fact that they've been lensed up from farther distances, I don't think that is accepted.
You think it's unlikely?
I don't think so. And I'm only quoting what I've seen in the literature from LIGO and other people. Now, the Hubble constant that's measured from LIGO, from this one system, it's quite broad. It's consistent with 70 kilometers per second per megaparsec, but it's consistent with a lot of things. As more detections are made, the statistical uncertainties will narrow even further. And that's important because there's an emerging tension between Planck CMB results and Type 1a supernova results. So there have been many suggestions about why this could be there, but the ultimate, I would say, arbiter of this would be an independent method like gravitational waves, which is calibrated only by our understanding of gravity. And so that will happen in the future as more and more detections are made. Between 50 and 100 should be enough to pin down which one of these is closer to being confirmed. Now, what I've built is a technique that doesn't use any electromagnetic counterpart information at all. It uses only the gravitational wave signal. This is the mass function method and uses two of the properties from the gravitational wave signal. This is the luminosity distance and also the redshifted chirp mass. The chirp mass is just a combination of component masses of the system. Now, we measure this redshifted chirp mass from the phase evolution in the waveform. But if you have a good handle on what the intrinsic mass distribution is, you can invert that and get an estimate of what the redshift is. Say you measure a redshifted mass, which is 2.8 solar masses, and you know that the mass, the intrinsic mass, should be about 1.4. Then you've doubled your mass, which means that your redshift must be close to being 1, just from this relationship. Now, we luck out because the neutron star mass distribution in double neutron star systems is actually quite dull. They're all about 1.35 solar masses with a small spread. And so this allows us to do this kind of technique, producing candidate redshifts based on statistical arguments of the neutron star mass function. So that's what we're doing here, just measuring the Hubble constant by inverting this, getting a measure of the redshift here, and then dividing that by the luminosity distance. With 100 double neutron star detections, that can constrain the Hubble constant to about 15%. And future detectors in the 2030s, like Cosmic Explorer or the Einstein telescope, will have such a large distance reach that we can probe the dark energy equation state and how it's evolving. And that can be constrained to roughly 10% at that time. This is showing how the precision on the Hubble constant scales with the width. Obviously, narrower neutron star mass functions give you more precise constraints than the Hubble constant. Now, there are exciting future opportunities to apply this. The mass function method doesn't rely on any electromagnetic counterpart information. It's entirely statistical. So you're probing the Hubble constant simultaneously with the neutron star mass function. So not only can you say which value of the Hubble constant, CNB or the type 1a supernova, is closer to the gravitational wave result, you can also probe the neutron star mass function and potentially probe the equation of state of nuclear matter.
So, but if I think about this technique, not at redshift 0, but doing it as a function of redshift, it seems to rely on the mass function not evolving with redshift.
That's right.
And my understanding of the neutron star mass function, if you go back to that figure you had, is it's not a delta function.
It's
right
not.
There are some things that are more massive.
That's true.
And, this starts to, feel like all the historical techniques for studying expansion by redshift, that, whether it's supernova or go back to like galaxies as standard candles and Tinsley and Gunn, right? It's the critique of it, right? It's things evolve in redshift, and things at redshift 1 are different than the universe today.
Well, the neutron star mass function in these systems should be a product of their evolution. I'm not sure if there should be an evolution.
It evolves with redshift.
Right. In which case you would apply a more detailed model which accounts for that evolution. And it's adding more complexity, but as long as you're accounting for that complexity, it's going to widen your estimate of the Hubble constant. All of that source of uncertainty will be propagated through, and you'll recover that in your
Yeah, I mean, I'm not concerned at redshift 0.1. It's when you have.
It's when you go to
redshift.
Einstein telescope or something. I agree. There are other things there you have to take into account, like weak lensing of the gravitational wave signal at those higher redshifts.
I would say there's also no guarantee that the neutron stars that we're seeing merging are exactly the same population of neutron stars. You see binaries something out.
Right, and that's why you don't lock it to what we see here. We allow it to be inferred simultaneously with the Hubble constant. Ultimately, the gravitational waves will tell us.
So I'm missing that point. Your H0 measurement is depending on the mass of the neutron stars that are merging? Or?
Well, the width of the neutron star mass distribution, because what we recover from the gravitational wave signals is a redshifted mass quantity. And so if you've got a very narrow neutron star mass function, then any spread you see across the population must come from redshift-dependent effects, which you can pin down and use simultaneously with the distances to get the Hubble constant. Okay, now as I said, next generation detectors like Cosmic Explorer and Einstein Telescope, I believe this will be the standard workhorse for cosmology, gravitational wave cosmology in this era, because we won't be able to associate the gravitational wave detections with a host galaxy. The galaxy catalogs will be incomplete out to where we get gravitational wave detections. And it's the farthest events that actually give you the most information about the cosmology. And at those redshifts, we can start to probe the dark energy equation of state and also the underlying rate density, the evolving rate density of star formation. All right, so it's not just neutron star detections that can give us cosmology. You can also do this with so-called dark sirens, binary black holes. In this case, you don't have one unique host galaxy identified because you don't have an electromagnetic signal, but you can use all events within some sky error region. And that's what the Dark Energy Survey and LIGO and Virgo did recently, constraining again the Hubble constant to roughly 70 kilometers per second. However, there were 77,000 roughly galaxies within this error region, 6,000 had spectroscopic redshifts, and they were all treated equally. But as I showed earlier, not all galaxies are really equal in producing these kinds of heavy black holes. So you should really incorporate what kind of progenitor information you have. So this was what I'm imagining for the future. You will rigorously model the evolution of stars across different evolutionary paths and really pin down the progenitor conditions, not only in isolated evolution in the field, but also in clusters. Track the influence of the demographic properties of the black hole component masses, spins, redshifts, and then train some sort of neural network or Gaussian process to interpolate over your representative sample of simulations. Having used the LIGO Virgo catalog to constrain the progenitor conditions, you can actually upweight any galaxies which are more favorable in producing the kind of masses that you need, that you measure. And so this should give you a better estimate of the Hubble constant. You should really be upweighting low metallicity galaxies in this kind of averaging procedure. And so that's what I imagine for the future, that you'll be able to probe stellar evolution simultaneously with the kind of host environments for gravitational waves, giving you a better estimate of the Hubble constant. Now, somewhat of a non sequitur, but LIGO and Virgo can also probe black hole superradiance and ultralight bosons. So ultralight bosons have been suggested as a compelling candidate for dark matter. Observational signatures of this kind of process would involve some sort of ultralight boson cloud surrounding a black hole, which would tap the spin of the black hole, causing the black hole to spin down. And the region of the mass spin plane, this is the black hole mass, this is black hole spin. Depending on the mass of the ultralight boson in a cloud that's surrounding the black hole, you'll get regions in this mass spin plane that are actually depleted.
Can you say a word of what that instability is?
That is a theoretical instability that there's an expert in the room I can defer to.
It's just like in the Penrose process, you just extract energy from the Earth region, and because these conjectured particles have a mass, they get confined around the black hole, and they keep scattering around it and extracting this energy while slowing the black hole down.
What particle mass is favored for them?
So they're theoretically anything below like 10 to the negative 6 eV, but
Yeah.
for this purpose,
10 to minus 12.
up to 10 to the negative 11 or so, and that's why it's ultralight, because they're very, very light.
But not the 10 to the minus 22.
10 to the minus 22 gives you a different phenomenology with that alters, you can get condensates of the size of galaxies and other kind of stuff. But
I know that, but it doesn't give you this one.
It won't match to black holes because they're too large.
That's what I
They're
thought.
comfortable.
Okay, fine.
Yeah.
And I'll get back to
Ultralight, that's
I'll get back to the 10 to the minus 22 electron volt systems later. So any population analysis from LIGO and Virgo with a catalog of binary black holes in the mass spin plane will be able to constrain the mass of this kind of particle that's tapping the spin of the black holes. So it's another compelling reason why population and catalog analysis of LIGO Virgo is important. It can not only tell you about the astrophysics of the source population, but also about fundamental physics like this. So up until now, I've been talking about stellar mass black holes, neutron stars, and LIGO. But really, we need to take a broader view. If you think about how we started exploring the electromagnetic wave landscape, we started looking up at the universe with our naked eyes and simple optical telescopes that gave a very narrow range of frequencies that we could access. But as our technology and our capabilities increased, so did our grasp of a huge range of astrophysical phenomena, from the CMB to AGN jets, exoplanets, pulsars, you name it, has been studied across the entire electromagnetic wave landscape. And this kind of discovery process is also true for gravitational waves. At higher frequencies, at say 10 hertz to a kilohertz, you've got LIGO, sensitive to stellar mass black holes and neutron stars. But if we want to access even larger black holes, we need to start populating this discovery space down here. And this is where LISA and pulsar timing arrays come into play. LISA should be sensitive at roughly millihertz frequencies to massive black hole binaries of order 10 to the 4 to 10 to the 7 solar masses. At even lower frequencies, you've got my daily bread and butter, pulsar timing arrays, which are sensitive to 10 to the 8 to 10 to the 10 solar masses, using precision timing of millisecond pulsars over decade coverage to look for correlated perturbations in the pulsar arrival times that are caused by gravitational waves. This sensitivity curve here is from Nanograv's analysis in 2018 that I led for the collaboration, and this is projecting forward the IPTA sensitivity in the early to mid 2020s. We're cutting right into the landscape of supermassive black hole binaries. So let's move into that regime then. Pulsar timing arrays are sensitive to gravitational waves through the stretching and squeezing of space-time again, but it's stretching and squeezing the space-time between the Earth and a pulsar. As a gravitational wave propagates in, it will cause a deformation of the space-time, which will either advance or delay pulses away from our models, away from our expectations. The Doppler shifting to the pulse arrival rates caused by this gravitational wave perturbation will depend on some angular factors. You can ignore this and treat this as some sort of angular response, but also the metric perturbation. And it's not the metric perturbation really over the entire interradiant space-time, it's the metric perturbation difference between the Earth and at the pulsar. Now the Earth term, as it's referred to, is coherent across all of the pulsars. All of the pulsars will share this term. However, the pulsar term is really a measure of the metric perturbation when the gravitational wave passed thousands of years ago. And it's dependent on the distance to the pulsar and the frequency of the gravitational waves. So if we can coherently extract this through accurate measurements of pulsar distance, this is almost like temporal aperture synthesis. because it gives us a measure of the gravitational wave emitting system's evolution over thousands of years, even though we've only been observing pulsars for roughly a decade. What we actually measure here is the offset to the pulse arrival time caused by the gravitational waves. And that's proportional to the strain over the frequency of the gravitational waves. So if you plug in some characteristic numbers here, the strain is roughly 10 to the minus 15, the frequency is nanohertz, you get a perturbation which is a couple of hundred nanoseconds. So we need that level of timing precision in our millisecond pulsars for this to be feasible. Now there are lots of collaborations worldwide that are working on this. Nanograv is a collaboration that I'm affiliated with. It's the North American Nanohertz Observatory for Gravitational Waves, using the Arecibo Radio Telescope, the Green Bank Radio Telescope, and there are some timing operations in the Very Large Array, and also in CHIME in Canada. The European Pulsar Timing Array is a cluster of radio telescopes across different countries, including Effelsberg, Sardinia, several others. Then the Parkes Pulsar Timing Array is in Australia using one telescope, which is Parkes. There are also emerging pulsar timing arrays and research groups in South Africa, India, and even China. So the frequency regime that we're sensitive to is really set by our time series considerations. We're looking at pulsars over decades, and we're only coming back to the same pulsar every few weeks. So this is really long timescale monitoring of these pulsars. So that means that we have access to 1 over the total baseline of coverage, which is roughly 10 to 15 years. So that gives us access down to a few nanohertz. And then roughly up to Nyquist sampling, which is every few weeks, gives us access to a few hundred nanohertz. And as I'm sure you're not surprised by the title of this slide, the target population is supermassive black hole binaries. They're expected to be ubiquitous throughout the universe. Most massive black holes should contain a supermassive, most massive galaxies should contain a supermassive black hole. As galaxies merge over cosmic time, the black holes at their centers will sink within the common merger remnant through dynamical friction processes. And that's like a Stokes drag force, which is efficient down to roughly a parsec of separation. At that separation, it becomes very inefficient, and you need additional processes to overcome that final parsec hurdle to get you to the kind of separations needed for pulsar timing arrays to be sensitive. And those additional processes could be scattering events of low angular momentum stars, or the interaction with some kind of circumbinary disk, which will extract angular momentum and energy from the orbit.
It's actually an n-body problem, not a two-body problem.
Right, interaction of the black holes with the
And the other black holes that
Yeah.
make it much easier.
Yeah. Now there are a variety of different signal classes that pulsar timing arrays are sensitive to. I mean, it's all binary black holes, but they fall into different regimes. The target population, the target signal that we're exploring will be a stochastic gravitational wave background. We expect that to be detected first, and that's coming from the ensemble of lots and lots of signals from the supermassive black hole binaries. However, if there is a relatively nearby or a bright individual binary, that can be individually resolved, and its system can be characterized, its orbit can be characterized. Now, we're not directly sensitive to the merger process itself. The oscillatory process of the merger is too high frequency and will probably extend into the Lisa band. We are sensitive to a GR phenomenon known as the memory burst. The memory burst is a DC offset in the final spacetime caused by the merger process itself. It's been described as gravity's ability to gravitate. It's the gravitational waves back-reacting on the spacetime, creating a constant offset. And that's actually broadband, so that will fall into the pulsar timing array frequency sensitivity regime. Now, how do we detect gravitational waves this way? Well, we are looking for correlated perturbations to the radio pulse arrival times between lots and lots of different pulsars. We can't just look at one pulsar because intrinsic noise processes will throw us off the scent. So we have to look at lots and lots of different pulsars. We're hoping to pull out a very distinctive quadrupolar correlation signature between the different pulsars. This is known as the Hellions and Downs curve. We need lots and lots of pulsars to do this. So with one pulsar, we don't have a chance. We add more and more pulsars, we're actually populating this Hellions and Downs curve very, very well. It depends only on the angular separation between pulsars in the sky, and it's very distinctive. We can think of nothing else which will produce a kind of correlation signal between pulsars that looks like this. However, there are differently correlated processes that we have to worry about. All of our pulsar observations are referenced to global time standards, which may actually drift over long time scales. That'll be shared by all pulsars, and and will look like a monopole correlated process. So it's the same at all angular separations, regardless of the pulsar. And we also have to reference all of our observations back to the quasi-inertial reference frame of the solar system barycenter, which allows us to have a good model of the solar system ephemeris, so the solar system model. If we make errors in that, or there's some systematic uncertainties, then we'll be thrown off again. And we'll get a dipole correlated process between all of the pulsars. So it won't look quadrupolar, but it is troublesome. We knew we were going to hit these kinds of uncertainties. What surprised me was in the last couple of years, we did, and it was a significant noise source for us, particularly the solar system ephemeris. So let me now move on to how we can balance the solar system with pulsar timing arrays. What you're seeing here is the Bayesian posterior probability distribution of the amplitude of the gravitational wave background in this particular spectral model under different assumptions of JPL's solar system ephemeris model. So this stands for development ephemeris, and then there's a number. And they're released every few years, depending on different weightings of legacy data with, say, Galileo data or Juno data. All of this spacecraft data is taken into account in a global fit by JPL. What they don't do is issue uncertainties with that fitting process. So what we end up getting is a systematic offset or differences in the detection statistics and also our upper limits, depending on the particular version of the solar system ephemeris. If we assume that the Bayes factor scales roughly as the inverse of the PDF support in this lowest bin, then the Bayes factor actually varies by over an order of magnitude, depending on the particular version of the ephemeris that's used. This is really unsatisfactory. We can't be beholden to a particular version of the ephemeris if we want to claim a robust detection. So what I've built is something called Bayes FM, which sounds a bit like a radio station when you say it, but it's actually the first Bayesian solar system ephemeris. And that's a perturbative correction to Jupiter's orbit. It doesn't matter where you start from, doesn't matter which particular version of JPL's ephemeris you start from, you correct that. You just perturb the orbital elements and marginalize over those corrections. So this is actually on its way to being the first full model of the solar system that uses Bayesian statistics. And this gives us statistical uncertainties at Jupiter's orbit of about 100 kilometers, which is broadly similar to JPL's rough estimates of Jupiter's uncertainty.
Do you mean that pulsar timing does better than JPL in tracking?
I wouldn't say that. It creates a more robust model by actually accounting for all sources of uncertainty in the error budget. JPL does not issue any statistical uncertainties with its ephemeris files. It's simply a point. Jupiter's orbit is here, and here, and here, and here. What we're actually doing is constructing posterior trajectories of the orbit, simultaneously with all the noise processes in the pulsar and the gravitational wave signal. So it's a better way of modeling the solar system ephemeris.
So Gaia also must rely on the solar system ephemeris, particularly Jupiter's position for breaking. Are those uncertainties? Is the 100-kilometer uncertainty show up in Gaia? Do you know, or is that?
It's a good question. I'm not quite sure. I haven't thought about the Gaia problem as it pertains to this. The reason why we have to worry about this so much is we need 100-meter precision at the solar system barycenter. I'm not sure Gaia is that demanding, but again, I would hope to talk to some people about that.
I know that Jupiter gravitationally is distorting the stellar positions.
Yep.
Eddington effect, and that needs to be corrected for. I don't totally get it.
Okay, we'll talk to some people afterwards. All right, so this is going to be present in all of our detection pipelines going forward. We have to be careful of all of these sources of uncertainty, especially correlated uncertainties. The next step will be modeling clock errors, which we don't expect to reach too soon, but it's still on our horizon for mitigating. Now, what is our detection timeline? Like I said, we expect to hit the stochastic background first. Detection there is expected within the next 3 to 6 years, and with that detection will come 5 to 10% precision on the amplitude of that background, which will allow us to discriminate different models of, say, the MN-Bulge relationship, or even spectral constraints on final parsec dynamical influences. Nanograv, this is Nanograv Plus. Plus means that we have to continue expanding our array. We need a large and expanding array of pulsars to make this possible. And the IPTA will do even better and advance the timeline by a couple of years potentially. And whether we have pessimistic or moderate signal assumptions, that all falls within the next, say, 3 to 6 years. we'll start to see emerging signals from our noise. And these signals are not going anywhere. All of the action on LIGO happens in a few hundred milliseconds. These signals are present in our entire data stream and are not going to go away anytime soon. The coalescence timescale for these black holes is roughly of the order of mega-years, tens of mega-years. So they are always going to be in our data stream.
This is assuming only the currently timed pulsars, or are you assuming?
No, this is assuming an expansion rate of about 5 per year, which tracks what nanograv is achieving at the moment and what other pulsar timing arrays are achieving. Now, in the future, beyond the initial stochastic background detection, we can achieve detection of an individual binary. We will have roughly a 50% detection probability of an individual binary by 2027. With that, we'll broadly get sky localization of about 1,000 square degrees. And this is showing, if we have an SNR of 8, which would be a threshold detection, we might expect to get roughly 1,000 square degree localization. And unfortunately, these memory bursts, these amazing GR phenomena, are not expected to be a strong signal for PTAs, but they should be an excellent signal for LISA. So that's something to think about and explore in the future. Even without detection, we can probe the spectrum of gravitational waves and put upper limits on the different factors that influence the shape of the spectrum. The amplitude, the overall amplitude of this spectrum caused by binary black holes will be influenced by our assumptions of the black hole bulge relationship, the merger rate of the binary black holes, and then at lower frequencies, corresponding to larger orbital separations of the binaries, we may have the system still in contact with the ambient galactic medium. So you'll have interaction with stars, predominantly from the influence radius of the binary, then a circumbinary disk, which will influence the orbit of the binary, and then any residual eccentricity of the binary will also influence the shape of this spectrum. And again, this is contrasted with our upper limits at each frequency. This delta, from what looks like a spike here, is simply because we don't have sensitivity at frequencies of 1 over a year, because we're fitting the pulsar positions simultaneously. So we're insensitive to periods of a year. Now, this is something we've actually achieved so far. We put limits on the shape and the amplitude of the background, linking those to astrophysical processes. We've been able to constrain particular models of the MM-bulge relationship, showing that McConnell and Ma is about 2 times more probable than Cormandy and Ho of 2013. Now, the flip side of that is you can take one of these as a prior on the amplitude of your background and use that to lock this behavior up here at higher frequencies, constraining the lower frequency shape. So any deviation of this lower frequency spectrum away from the power law will indicate some interaction with the ambient galactic environment. So what this is showing us from Nanograv's 11-year analysis is that we're disfavoring any black holes that are highly eccentric and also in diffuse stellar environments. So we're more favoring some interaction with stars. And that's taking the Cormandy and Ho relationship as our prior for the amplitude of the background. This kind of recovery was done with another emulator. This emulator this time was from binary population synthesis of supermassive black holes, being driven by a combination of gravitational waves, stellar interactions, and gaseous disks. Now, it's not only astrophysics we can probe, we can also probe fundamental physics with PTAs. In a more general metric theory of gravity, we can have 4 additional polarization states, which will have different correlation signatures between the pulsars. Broadly, the usual GR modes will give a constant relationship in the autocorrelation as a function of frequency and distance to the pulsar. But if you've got something like a scalar longitudinal mode, so this is deforming the space-time along the direction of propagation, you'll get a strong dependence of the correlation as a function of frequency, gravitational wave frequency, and the distance to the pulsar. So we can use these correlation signatures to constrain additional modes of polarization in the gravitational wave signals. And the fact that we have such a strong dependence on frequency and distance here in this mode means that we can constrain the amplitude of such a mode 2 orders of magnitude better, this is 10 to the minus 17, better than the GR modes at about 10 to the minus 15. So expect to see a Nanograv limit paper on alternative polarization states in the future. It's not just the spectrum of the gravitational wave polarization states we can probe, we can also probe the sky angular distribution. We can do power mapping in GR using the usual correlation signatures between 2 different pulsars. This is showing an example of a recovery of a gravitational wave sky composed of lots and lots of binaries. You see bright binaries popping out here. If we model the sky as some sort of basis of spherical harmonics, and we're recovering the weights, we can broadly recover where these binaries are. And this is going up to a multipole of 5. So this is similar to temperature mapping of the CMB. We're just using the expected cross-correlation signature between the pulsars to extract what the map of the sky is. Now we can go beyond power and actually map the amplitude and polarization content of the background. This is something that I worked on with Chiara and some other people, including Jonathan Guerre and Joe Romano. This is splitting the metric tensor up into parity even and parity odd modes, very similar to polarization mapping of the CMB. In fact, that's where the analogy came from. We decomposed the metric perturbation onto spin-2 spherical harmonics, finding that PTAs are actually insensitive to tensor curl modes. And that's because we essentially have a static detector, so we can't break certain degeneracies that would give us sensitivity to those curl modes. We can even extend this to alternative polarization states, mapping the content of these alternative skies, finding that PTAs are actually insensitive to any structure in a scalar transverse sky that goes beyond dipole. So there's a whole small-scale structure landscape in alternative polarization states that we're not sensitive to. Now, some exciting future opportunities, I think, come with tethering individual supermassive black hole binary hunting, the PTAs, with large time domain surveys. So existing searches for individual sources of gravitational waves by nanograv have actually constrained any binaries closer than 120 megaparsecs at 10 to the 9 solar masses. If they were closer than 120 megaparsecs, we would expect to see them. Likewise, if there are any binaries of 10 to the 10 solar mass that are closer than 5.5 gigaparsecs, we would expect to see them. We've also constrained the fact that there are no binaries more massive than roughly 2 times 10 to the 9 solar masses in the Virgo cluster. So this is representing roughly our sensitivity to gravitational waves coming from different parts of the sky. And this varies by roughly an order of magnitude across the sky, and is highly sensitive to our placement of pulsars. So we're sensitive mostly to where we have the pulsars. Unfortunately, a lot of the compelling candidates for individual binaries are on the other side of the sky. So we need targeted pulsar searches that actually fill in this region of the sky, giving us better sensitivity to these compelling candidates. And we do expect there to be electromagnetic counterparts to these systems. Unlike LIGO, where there's no gas hanging around the binary black holes, there's expected to be quite a bit of gas hanging around supermassive black holes. After a galactic merger, a lot of materials will be channeled into the galactic center, forming accretion disks. And that has a variety of different possible signatures in UV and optical campaigns. This is a diagram from one of Luke Kelly's recent papers showing that accretion processes onto the primary and secondary black holes should produce variability in the optical and UV over orbital timescales. For hydrodynamic variability, we've got periodic variation in the accretion onto the primary and secondary. If you've got equal mass binaries, the kind of timescale of variability is close to 5 to 6 times the orbital period. But if you've got low mass ratios, it's similar to the orbital timescale. If you've got Doppler boosting of radiation from a secondary's mini-disk, then that will actually be on the orbital timescale of the binary. So these are compelling electromagnetic signatures that can be hunted for with future time domain surveys, like LSST, where you'd expect there to be several hundred of these optically variable systems. We already have long baselines of these time domain campaigns, including from the Catalina survey, Palomar Transient Factory, and Pan-STARRS. And Zwicky Transient Facility is operational now. So the goal will be to build a very long baseline connecting on to LSST. And then after 5 years of LSST operations, we should have several hundred binaries which are detectable as hydrodynamically variable or Doppler boosted binaries. And 5 years of LSST data actually takes us up to when we'd expect the first individual binary detection by PTAs. So this actually tracks very well and allows us to do coherent multi-messenger searches for individual binary black holes. In addition, spectroscopic surveys of quasar broadlight regions can give evidence of binarity, and this is something that's a target of SDSS-5, in particular the black hole mapper component of that. So the goal is to take a multi-messenger time series view of these PTA and time domain surveys, fusing them together and actually improving our understanding of accretion processes around supermassive black holes. So we'll have them tracked in gravitational waves and also in time domain surveys in the next decade. So we can also probe dark matter with PTAs. That was a very rough segue, but nevertheless, As has been mentioned, any dark matter that has been proposed as an ultralight scalar field and happens to be of mass 10 to the minus 24 to 10 to the minus 22 electron volts will actually produce a signature that PTAs are sensitive to. What this does is produce an oscillating gravitational potential which alters the arrival time of radio pulses and is shared between all of the pulsars in the Milky Way. So what's happening here is that at such low masses, the de Broglie wavelength is actually of order hundreds of parsecs, if not kiloparsecs. So you form a condensate that's oscillating. And the frequency for this kind of mass particle, which would be an axion, lies right in the nanohertz band, where we could probe it as a spike at nanohertz frequencies. This is a quick analysis that I put together, constraining the oscillating component of the gravitational potential as a function of the mass of this kind of axion. And this is already, with nanograv data, we're getting some improvements over existing constraints on this. But the IPTA, everyone working together, will really hammer this down and give us much, much better constraints on dark matter. Now, this is a particular version of fuzzy dark matter. Fuzzy dark matter is generated to solve the small-scale structure problem, where standard cold dark matter predicts that there should be more structure in smaller scales than there is. Fuzzy dark matter should mitigate that. It's a possible solution. But even within standard cold dark matter theories, any form of dark matter substructure can be probed by PTAs. If you've got lots of subhalos along your line of sight, then you'll have the pulses propagated through some gravitational potentials.
What mass subhalos are you thinking of?
I'm thinking 10 to the minus 11 solar masses, pretty
No.
small.
Wait, the subhalo masses.
Yeah,
10 to the minus.
solar masses.
10 to the minus 11?
Yeah, I believe so here, yeah. That too small?
That's pretty small.
Well,
Those subhalos don't exist at fuzzy dark matter.
no, this is within cold dark matter.
That's CDM.
Yeah.
Okay.
I'll check, but I might have gotten that figure wrong, but I'll check. So this is standard cold dark matter. This is propagation of the pulses through some sort of potential involving subhalos. Even with a subhalo that's hanging around a pulsar or near Earth, that will also induce some sort of acceleration on the Earth of the pulsar, which can generate some sort of Doppler delay to the pulses. Now, this is another exciting opportunity to use Gaia to at least constrain gravitational waves, if not detect them. Gaia may lack the sensitivity to actually detect gravitational waves at nanohertz frequencies, but it can be used to cross-validate. So Gaia is looking at the positions of roughly 2 billion stars throughout the galaxy over 5 to 10 years. And so this would be using the spatial part of the deflection 4 vector to constrain the influence of gravitational waves. And actually, from some preliminary estimates, the sensitivities shake hands pretty well. There's a crossover in the frequency regime between pulsar timing arrays and Gaia. So even if Gaia is not competitive at lower frequencies, where pulsar timing arrays are expected to be dominant, they could be sensitive to higher frequencies, where PTAs start to rapidly lose and diminish their sensitivity. So this gives us the opportunity to, again, constrain alternative polarization states, because the correlation signatures similarly scale with frequency and distance, but also corroborate a PTA detection of nanohertz gravitational waves. Because Gaia really is the only other detector that can access the nanohertz band of pulsar timing arrays. So having some sort of spatial version of corroboration will be very important. All right, in summary, gravitational wave observations across all frequencies will probe supermassive black holes and stellar mass black holes at a dramatically varying different mass scales. LIGO and Virgo has given us access to stellar mass black holes and neutron stars, allowing us to probe physics of stellar evolution and also cosmology. And the opportunities for the future there are to really pin down what the Hubble constant is, using a one-run alternative to cosmological distances, constraining the physics of different evolutionary paths, and also probing ultralight boson dark matter particle candidates in the mass regime 10 to the minus 12, 10 to the minus 11. Pulsar timing arrays will have access to the most massive compact objects in the universe, populating the lower regions of the gravitational wave landscape and allowing us to understand the large-scale demographics and small-scale dynamical interactions of supermassive black hole binaries. The opportunities for the future there are tethering those constraints with synoptic time domain surveys in the next decade, and actually tracking the gravitational wave and electromagnetic behavior of supermassive binary black holes. And then there were some other alternatives I threw in at the end there involving constraints on dark matter, in particular fuzzy dark matter, and also potentially shaking hands with the Gaia sensitivity curve to actually corroborate nanohertz gravitational wave detection. So there are exciting opportunities for the future. I think this future will cover the entire range of possibilities in frequency and mass space. And watch this space.